here's what I want to think about. In that dimming drama that we did in class, there was chatter going on that really had nothing to do with the X-bar charting. It was chatter about whether the individual observations were less than 3 or bigger than 7. Let's think about that situation. So dimming drama, the specifications were supposedly a lower spec of 3 and an upper spec of 7, and the interpretation that we made in class was that a 3 was okay, a 7 was okay, but a 2 or an 8 were not okay. Let's ignore the fact that as a matter of fact, that those bags of washers have only integer values in them. So let's ignore the discreteness of the actual brown bag process. And pretend that the brown bag was exactly normal. So we're going to pretend that it's continuous. And let's further go ahead and do this. Let's think about, just for sake of illustration here, not because it's really a good idea, but for sake of illustration, let's think about a P charting example. So think about P charting based on the sample size that was used in the dimming drama. So let's think about P charting based on n equal 5 for this scenario. Now, if one takes a normal distribution that's representing the brown bag, so if this is the brown bag process, and I think of it as normal with mean 5 and standard deviation 1.715, that's sigma. And if I come down here to 3 and I come up here to 7 and think of these things as my specifications, then if I take this area plus that area, so these together represent a fraction of the population that is non-conforming. Okay, so if you ask yourself what fraction of those washers in that brown bag are outside the limits 3 to 7, at least if I ignore the discreteness of the bag, what I need is those two normal probabilities added together. That is, I need to make a couple of z values. The first is 7 minus 5 over 1.715. That's the z value for this upper specification. That turns out to be 1.17, and the second z value is 3 minus 5 over 1.715, and that's minus 1.17. And so my point here is that the probability a washer is out of specifications is then approximately the probability that a standard normal variable is less than minus 1.17 plus the probability that a standard normal variable is bigger than 1.17, and that is about 0.2420. Okay, and in a p-charting context, if I want to go from thinking about doing x-bar charting to doing p-charting, there's my standard. There is the standard value of p. So for control charting, for p hat based on, say, a sample of size 5, the upper control limit for p hat is going to turn out to be 0.2420 plus 3 square roots of 0.2420, 1 minus 0.2420 over the sample size, which in this case is 5. That is 0.8166. Now, 81.66% of a sample of size 5 is more than 80% is more than 4 out of 5. Okay, so I look at this thing and I see that only samples with p hat of 1 will plot outside control limits. That is, if you come back up here, you change that plus sign to a minus sign, you're going to get something negative for a lower control limit. The upper control limit is bigger than 80% is bigger, that corresponds to more than 4 out of 5 plotting outside of limits. So that says only samples with p hat values of 1.0 are going to plot outside of limits. Okay, so what does this mean? Well, this means, for example, that if all is okay, and I mean by that, i.e. the mean is at 5 and the standard deviation is at 1.715, just as were used to set up the control chart, then what is going to be the average run length? Well, then the ARL is gotten as follows. I need this value little q. That is the probability that the first plotted point plots outside limits. in this particular application, what's going to be plotted are sample fractions non-conforming, and that then means that all 5 items in a sample are non-conforming. Well, how can that happen? The first one has to be non-conforming, and that happens with probability 0.2420. The second one is non-conforming. That happens with probability 2420. 0.2420 for the third one, 0.2420 for the fourth one, 0.2420 for the fifth one. That is, I've got this I've got the fifth power of p here. That is, this is p to the fifth power, and that's a binomial probability. That is, I told you that we were going to use the binomial distribution. This is the probability of 5 successes in 5 trials, where a success means that the item is a non-conforming item. Well, if you do the calculation, that turns out to be a pretty small number. That is 0.00083, and that means that as we've set this thing up, the average run length for this example, if everything is as we thought it was when we made the control limits, the average run length is 1 over 0.00083. It's 1,205. So we're going to wait on average 1,205 trials before we get a sample that has 5 non-conforming washers in it. That's extremely conservative. You might ask, well, what if we went back and redid this problem, changing things up and using a tighter control limit? That would be a good exercise for you to do there at home. Do the probability that you get 4 or 5 in a sample of size 5 that are non-conforming. That would correspond to a upper control limit for p hat that was below 0.8, but bigger than 0.6. I'll let you work that out on your own. What I will do here is, for example, to see what happens if the process mean shifts by, say, 1 standard deviation, so that we've got something that's similar to the X bar chart calculation that we just did. So on the other hand, if the process mean shifts by, say, 1.715 from 5 to 5 plus 1.715, okay, to 6.715, then what happens to this average run length? So now, in terms of individuals here, here's 3, here's 7, And now we've got a mean that's really very close to this upper specification. So this is U, this is L, this is 6.715. What I'm showing you here is the distribution of individuals. This is the process distribution now, where the standard deviation is still going to be 1.715 for this what-if calculation. And now, though, the probability non-conforming, our P, is going to become the sum of these two things. So P is the sum of these, and that means that I need a couple of z values. I'll need a z value for 7, where the mean is now at 6.715 and the standard deviation is at 1.715. And that z value turns out to be about 0.17, and I'll need a z value for the lower specification, so I'll need a 3 minus 6.715 over 1.715, and that is about minus 2.17. Okay, so that means that the fraction then out of specifications is the probability that a z value is less than minus 2.17 plus the probability of getting a z value bigger than 0.17, and you can check that that is about 0.4475. So if one is in a situation where the process mean is not at 5 any longer, but is at 6.715, that changes the fraction non-conforming to the sum of this and that is substantially larger than it was with that distribution centered at 5. In fact, it is this much. Okay, so that means that this probability that a first point plots outside of control limits is a probability that the first sample has all defective or non-conforming items in it, so all 5 items in the first sample are outside specifications, and that is now 0.4475 5 times. Okay, and that is 0.0179, and that means that the average run length in this context is the reciprocal of 0.0179. That is on the order of 56. What that says is that even though there's been a very substantial change in the process mean to where 45%, 44%, 45% of what is being made is now non-conforming, it's going to take you, on average, 56 periods, 56 sampling periods to detect that. This is pretty big. Okay, this is pretty big considering that P has gone from, or P has gone 2.4475. Okay, what's the point? The point then here is that we've got a way of quantifying and thinking about, well, does it make sense to do P charting in this context instead of doing X bar charting? This average run length calculation suggests, well, that may not be such a good idea because we're going to be a long time catching a rather substantial process change if what I'm doing is P charting based on samples of size 5 in this context.